Hello, everyone. Thank you for joining today. I am super excited to uh, introduce this panel discussion on stratospheric aerosol injection. My name is Jeremy. I am a PhD candidate at Stanford, and I will be moderating this discussion today. I wanted to start by thanking Lina Kipp, my co-organizer who helped me organize this event, as well as Daniel Vizioni and Duncan Watson-Paris for all their input on the event as well. Thank you so much. So, like I said, very excited for this panel. We have really an amazing set of panelists joining us in the discussion today. I will give a very brief introduction to each one of them. This introduction is going to be too brief. Each one of these panelists really deserves so much to be said about them, but I'm going to keep it brief so we can dive right into the discussion. So to start with, Chris Field is the director of the Stanford Woods Institute for the Environment and a professor of Earth System Science at Stanford. He is globally recognized for his groundbreaking research on climate change impacts and his leadership in the Intergovernmental Panel on Climate Change. David Keith is a professor and the founding faculty director of the Climate Systems Engineering Initiative at the University of Chicago. He is a world-renowned expert on solar geoengineering, particularly stratospheric aerosol injection, and has been a driving force behind advancing research in climate intervention strategies. Douglas McMartin is an associate professor at Cornell University's Sibley School of Mechanical and Aerospace Engineering. He's a leading researcher in solar geoengineering, focusing on the modeling and evaluation of climate intervention strategies like stratospheric aerosol injection to better understand the potential climate impacts and inform policy decisions. Andrew Ng is the founder of Deep Learning AI, founder and CEO of Landing AI, chairman and co-founder of Coursera, and adjunct professor at Stanford University's Computer Science Department. He is a pioneering figure in online education and artificial intelligence, significantly advancing deep learning and its applications across various domains. Simone Tilms is a project scientist at the National Center for Atmospheric Research and a prominent researcher in stratospheric aerosol injection. Her work focuses on the impact of geoengineering on the Earth's climate, particularly its effects on stratospheric chemistry and the ozone layer. So thank you all again for joining us today. Before we get started in the discussion, I wanted to give a quick primer on how this is going to be formatted today. We're going to start with a 70-minute, roughly, panel discussion covering various aspects of SAI and a dedicated 10-minute Q&A at the end of the session. That being said, please feel free to post questions in the Zoom Q&A system throughout the panel. We will try our best to raise some questions throughout the panel, but like I said, we will certainly have a dedicated Q&A session at the end. Okay, with that, let's go ahead and get started here. So to kick off the discussion, I think it'd be helpful to start with just explaining what stratospheric aerosol injection is and why it's considered a significant tool for managing global temperature. If anyone would like to start us off, that'd be great.
Maybe I could start out with a pre-issue, which is the real crisis we face from a warming climate. Last year, 2023, was by far the hottest year in the instrumental record. It was nearly 0.2 of a degree Celsius warmer than the previous warmer year, which was 2016. It was approximately 1.4 Celsius higher than pre-industrial. And we're still in an era where emissions of heat-trapping gases are continuing to increase. They're not decreasing. And we know that warming won't stop until those emissions drop all the way to zero. We also were seeing an incredible abundance of the severe impacts of the climate change that's already occurred. And we're seeing more and more benefit in being able to address the amount of warming. Now, were we not in this crisis of a warming climate, we wouldn't even be having the conversation about using interventions to cool the Earth. And I think it's important to start from the framework of how serious the climate challenge is and how we're currently on a trajectory where we might see twice the amount of warming we've already seen, something like 3 Celsius, by the time we get to 0, under the kind of commitments that have been made and the adherence that we're seeing through those. Just want to start us off with the recognition that the climate crisis is serious and it's immediate and it needs attention through every lever that we have available to us. That's why this one deserves attention.
I think that's a very fantastic point, a great way to tee off the discussion today.
Yeah, maybe I can start just simply to say where does the idea come from and what it is. Basically, the idea came from observing large volcanic eruptions and their effects on the climate system. So all the time in the past, in our history, we had volcanic eruptions, and some are very strong and big, and that means they provide a lot of ash as well as gases all the way up into the stratosphere, meaning above the troposphere, the cloud layer, into the stratosphere. And the last large volcanic eruption we had was in 1991, the Mount Pinatubo eruption, that transported about 10 or 15 teragrams of sulfur into the stratosphere, a gas that then in the tropical regions, that then basically gets transported around the globe. It forms aerosols, sulfate aerosols. They get transported around the globe with the stratospheric circulation. And basically we have a shield, a cover that is around the Earth of particles, of aerosol particles. And what happens is that people observed after these large volcanic eruptions and significant cooling of the Earth's surface. And for instance, the idea is that the sunlight is in part, a small fraction is reflected, the incoming sunlight. So less will basically reach the Earth's surface, we get some cooling. After Mount Pinatubo, an average or an approximate cooling of 0.3 degrees Celsius has been observed or identified. And so the idea is that that's something that maybe could be used to also help to counter some of the impacts of warming climate. And in that way, what we would have to do, though, is not imitate a volcano. A volcano erupts wherever it wants, and it only erupts, at a certain point in time and injects a certain amount of gases or aerosols. But the idea is really to inject continuously in the stratosphere so we can cover the globe, for example, in some way that we reach some cooling of the Earth that we want to achieve. And you have to do it. Volcanoes, for instance, erupt once, then they get transported and the material gets rained out after a few years. But if you want a continuous cooling, you have to reply more and more materials into the stratosphere in order to keep that cooling. That's just the start, and maybe others can jump in and continue.
I'll offer another piece of kind of context complementary to what Chris said. I think there are really only 4, in a kind of high-level categorization, 4 categories of things humans can do to reduce climate risks. The first of those is to cut emissions, to decouple industrial activity from emissions. That's the most important in terms of action now. The second is we can remove carbon dioxide from the atmosphere. I think there is no reasonable doubt that this could be done at scale, and that in fact it would be possible in principle to, over the next century or so, remove all the carbon dioxide that we put in the last century or so. The third thing is the topic here, solar geoengineering, or whatever you want to call it, the idea that we could make the Earth a little bit more reflective to reduce some of the heating and other climate impacts that come from the accumulation of greenhouse gases. And the fourth are all these local adaptive activities that reduce the harms that a given level of climate change causes to humans and ecosystems. And I think my biggest message maybe for people who are coming to this new is that we need to think in 4 dimensions. These really are the 4 ways we can solve the problem. There's a myriad of different individual technologies and political ways to get to there, but these are the 4 high-level categories. And finally, none of this is new. So these categories were in slightly different language in the very first IPCC report. These ideas we're talking to you today about solar geoengineering, or under different names, go back for more or less half a century. So this is not something that we just thought up, but we're now, I think, at a point where it's important to talk seriously about these all four dimensions and to think about how they fit together to provide a less risky planet for humans and for the non-human inhabitants.
Great.
I
Just
think the only thing I would just,
go ahead.
David said it, I would just, really emphasize when we're talking about this, it's not a substitute for doing other things. It's something that you would do on top of it. In some sense, the reason that this conversation is happening now, it happened a little tiny bit 10 or 20 years ago and 30 years ago. The reason that it's more clear now is that it's, I think 20 or 30 years ago, it was a lot easier to be optimistic that cutting emissions alone would be sort of good enough. And now, as Chris said, we need to do better on cutting emissions, but there is going to be significant climate warming in the meantime. And the big distinction between solar geoengineering and something like carbon dioxide removal is that the solar geoengineering is fast, right? You cannot remove all of the historical emissions that we've put into the atmosphere on a dime. And if you could, that would really solve the problem. Whereas you can do that slowly over a century and in the meantime cool the planet.
Yeah, maybe two adding on top of that, I agree with all of it. One thing I think it's important to say is I think we are making huge progress in cutting emissions in a way that really is different than a couple of years ago. And I think it's important not to frame this as we've got to turn to SRM as plan B because we failed on plan A. That's a common framing and it's completely wrong. We have to cut emissions. And I'm actually quite optimistic. I'd be willing to make monetary bets with people that we will see the peak of emissions this decade. That doesn't mean that they will fall as quickly as lots of people might hope, and I would hope. But still, after 150 years or more of fossil fuel-driven industrial civilization, to be able to peak emissions while people's livelihoods still get better is a fantastic achievement. And I think it's likely within our grasp this decade. So there really is progress.
And maybe adding one thing, the peak of emission doesn't mean the peak of temperature. What we will see is we can only stop the temperature increase when we stop all the emissions. When we are at net zero, then we don't increase the temperatures. We do have concentrations in the atmosphere, greenhouse gas concentrations that will continue to rise if we increasingly putting stuff in there. And then as soon as we reach net zero and then to go towards negative emission potentially, then temperatures will also further go down. And negative emission means naturally that the globe absorbs these greenhouse gases again naturally, but also as we talk about CDR, but this is not the topic here.
One last thing to say is that
Go ahead, David.
any of these pathways have risks. There's no risk-free pathway. Cutting emissions extremely rapidly, it's easy to say we just should want that and we should have enough desire to do it's the right thing to do. But cutting emissions very rapidly has risks, especially for people in developing countries who want to develop through access to clean energy. So that's not a statement that we can't cut emissions. We absolutely can. Zero is the right answer and we'll get there. But there are risks to going too fast. Large-scale carbon removal is possible, but doing it very quickly will have big environmental impacts. Solar geoengineering will have risks, as will various adaptation methods. So in thinking in 4 dimensions, this is a choice between different risks. And I think a view that I have, I think many of us has, is that people underestimate how useful solar geoengineering might be and tend to overestimate how risky it might be.
Wait, just add one additional perspective. I think decarbonization is critical. Over the years, whenever I wrote about climate change, not even stratospheric aerosol injection, whenever I wrote in newsletter, The Batch, about climate change, predictably, I used to get, and even now, a small amount of hate mail criticizing me for promulgating this climate change hoax. And then, I'm sure many of you have a similar experience too. Whenever I mentioned the possibility of studying SAI, stratospheric aerosol injection, I do get some number of messages saying, please don't do this. This is a bad idea. And I think that's just to address what may be one elephant in the room. Maybe the people that dialed in are already friendly to this idea, but I think society has a somewhat negative view, instinctual, emotional, negative. It's like a guttural reaction to who are you to play God to engineer our planet this way to try to cool it down. One thing that quite moved me earlier this year was when we were reading in the news reports about over 1,000 people dying in Mecca because of heat-related deaths. And while I know it's difficult to attribute any single death to climate change, there are enough news reports of people dying heat-related deaths that I feel like we're in a position where we don't have great options. And even in California, where I am, I think over a 10-year period, almost 500 people in California, pretty advanced economy, died from severe heat events. And I know there's an attribution problem and so on. But when we read in the news about the warming planet and people literally dying, literally the end of the road for those individuals, I feel like we have a responsibility to look at the sometimes not so great options ahead of us and pick what seems the most responsible for our fellow citizens of the planet. One thing one thing I sometimes think about, I have 2 young children, and when I look at them, if we don't, on the current forecast, even with strenuous decarbonization efforts, many of the forecasts are it's just going to get worse over their lifetimes. If SAI, stratospheric aerosol injection, turns out to be infeasible, and the decarbonization proceeds on maybe even the slightly more optimistic forecast that we have. So one of my personal real fears is I actually really worry. My kids are 3 and 5 right now, too young to understand climate change. I do worry if someday my kids will grow older, planet with a disaster. It looks like we're headed toward, 2 to 4 degrees of warming, right? 1.5 degrees is dead. So let's say 2 to 4 degrees of warming. And someday my kids will ask me, hey, what did you do when we had a chance? And I hope we can have a good answer to them. And I think stratospheric aerosol injection, not great. I wish we didn't have to do it, but of the different realistic options we have, and the current option is people are dying. This seems like a plausible alternative to be at least worth seriously considering. And one other interesting effect that I've seen is I think the climate scientists call, you're all experts on this. If anyone's wondering, boy, isn't this a dangerous thing to start? The interesting thing is we've actually been doing negative stratospheric aerosol injection because of things like removing sulfur from shipping fuel. So over the last several years, we've actually been reducing aerosols in the atmosphere, mainly because to reduce certain types of pollution. And this seems to be contributing to accelerated warming. So not only are we not injecting aerosols to cool down the planet, we're actually removing aerosols in a way that is probably accelerating the warming of our planet. And so I think looking at this set of issues with a scientific perspective, AI climate modeling, various other things, to figure out what is the most rational path seems like an important set of decisions for us to make at this point.
Andrew, your comments on the progress we've made with sulfate pollution are really important. Air pollution is a major killer, a much larger killer than climate change in the current situation. And one of the things that we really need to think hard about as we look at options that involve injecting additional pollutants in the atmosphere is whether we increase the pollution burden by more than we alleviate the climate burden. And one of the advantages of the stratosphere is that the lifetime of whatever is injected in the stratosphere is long relative to being in the atmosphere close to the surface. And it's not necessarily the case that we would be increasing the pollution burden overall by injecting sulfate into the stratosphere, but it's an important issue. And calculations that David and others have done indicate that we likely would see some additional deaths as a consequence of additional stratosphere sulfate. but that those would be a tiny number relative to the number who are already killed by air pollution. And if we think of this technical challenge as decreasing the release of sulfate into the atmosphere near the surface and moving a little bit of it to higher in the atmosphere, we're resulting in an overall decrease in deaths from air pollution. At the same time, we might be able to achieve substantial relief from the climate impacts. And that's really the research question that still needs to be addressed.
Picking up on that, some very rough numbers. So all in rough, simple numbers, but roughly aerosols last in the stratosphere for about a year, and aerosols last in the lower atmosphere for about a week. So the ratio of 50 to 1 in lifetime. So what that means is more or less, to have the same amount of aerosol cooling, you'd have to pump aerosols in, all else equal, at a kind of 50 times higher rate in the lower atmosphere than in the stratosphere. Then there's a second fact that's not so obvious, is that if you think about the health impacts of a given amount of aerosols pumped into the atmosphere, it turns out it's about 20 times less for aerosols pumped in the stratosphere than it is for aerosols pumped with the current distribution of pollution sources. And that's largely because this stuff falls out of the stratosphere, it mostly rains out, forming acid rain, but that turns out to be a tiny thing, but it mostly doesn't reach the ground as particulates. So 50 times 20 is 1,000. And very roughly, there's big error bars on these things, but when we've tried to use pretty standard models of air pollution chemistry, we find that if you put a kilogram of sulfur in the stratosphere compared to a kilogram of sulfur with the current emission sources, the ratio of the cooling benefit to the air pollution harm is about 1,000 times more favorable, that ratio. That is, the cooling is 1,000 times more per unit of air pollution harm, roughly, for stratospheric aerosols compared to the existing air pollution aerosols, which are both killing people and cooling the planet.
Very
And-
interesting.
Go ahead.
Okay, yeah, solid, yeah, very interesting comments. I think it'd be helpful to talk a little bit more about how we understand these effects. So what models do we have? Roughly, how do they work, and how reliable are they?
Yeah, maybe I can start doing a lot of modeling with the global Earth system model. What we use for modeling stratospheric aerosol intervention is the same models often that we use for also climate change modeling, but they have to be more sophisticated in some way. So when we look at climate change, we often, we look at the future and say, these are the changes, the future changes given through certain emission scenarios. If we want to simulate really the effect of something that goes in the stratospheric aerosol or gases, we have to simulate the processes that are happening to do that. So we have to have a well-resolved stratosphere in those models, and not all of these climate models have that. We have to have a very comprehensive way to say, how do these aerosols form? How do they transport? How do they interact with chemistry? And how do they come down? And actually, we understand quite a bit, actually, because when you think about it, in the 60s and 70s, we had the start of the ozone hole. The ozone hole had been discovered. There was a lot of research funds going into developing models that can simulate the stratosphere, as well as the Earth's climate itself. But it had been focused on this, and there was a lot of understanding already. How does the chemistry work? And, there was Mount Pinatubo erupting in 1991, what I said, and people also looked at the interactions with aerosols and chemistry at that time. So many models can actually simulate more or less comprehensively stratospheric aerosol intervention in form of they prescribe some kind of aerosol layer like they do for volcanoes, or they can do it more interactively. So there's a range of complexity. And therefore, I think there is actually a fairly good understanding if we, for this topic, use sulfates, because that's what we have learned and observed from volcanic eruptions. This is not the same when you think about other materials, which we haven't touched on yet. But of course, there is no reason that we need to submit sulfate or use sulfate for stratospheric aerosol intervention. And as we may talk about later, sulfates have their side effects. they do impact ozone, they do absorb radiation, they heat the stratosphere, they have certain impacts on the dynamics, on the climate, triggering down. And we can talk about it more later. And that's why people also think of other materials. They may have been more beneficial. David has started those ideas with the group at Harvard on thinking of calcite, thinking of other materials that may not absorb so much. So there's a whole question on that because those materials have not been studied that well. What I also want to say quickly is that you have to think about the climate model we are using are really comprehensive also in regard to simulating the whole Earth system, right? Going from the atmosphere to the ocean to the land, they couple things. They are comprehensive. But if you asked, of course, researchers about uncertainties and things we still need to do, there's a whole lot of things we still have to study, we still have to put into these models because they are never perfect. They are not a second Earth as people want to have. They are parametrizations, they are models that run 100-kilometer grid sizes basically as one grid point. And so it is always something that is a simplified parametrization in those models.
I want to pick up, I think Simone probably agrees with me, but I'll just jump in. I think you said things we have to do better. So the job of science is to find problems that are unresolved and fix them in the models. And you and others on this call are doing a great job of that. We all do versions of it. The models have, anybody who uses them knows all sorts of problems with them. But I think it's important to say that the reality of decision making is decision makers have to make decisions in the face of uncertain information. And you could say, and you might even want to say it if you were an apologist for Exxon, that because there are uncertainty in the models, we shouldn't make decisions about climate change at all. We shouldn't cut emissions until we know exactly how much given carbon dioxide emissions will warm the planet. Of course, I'm not saying someone thinks that, but it's important to say that the fact that there's uncertainty isn't a reason not to make decisions, because decision makers make decisions with uncertainty. And it's important to say, as Simone did say, that the uncertainties in the models for response to sulfate aerosols these are very much the same models as are used to look at response to CO2 and other greenhouse gases. It's not exactly the same problem, but it's highly coupled, and the uncertainties are coupled and in some senses of a similar order. And I think the hard question is, we as scientists can always think of things we'd like to know better, but the question ultimately not for us, but for policymakers is, what level of certainty do they need about SRAI before they want to make decisions?
It's probably worth talking just a little bit more about how good or bad the climate models are. And climate modeling is something that we as a community have been pursuing now for half a century. The models are increasingly highly resolved. They're based on fundamental physics that are understood, and they're really good at many things we care about. They're really good at getting the global average temperature. And they're really not very good at a lot of other things that we also care about. And so when we have this conversation about consequences of stratospheric aerosols for global average temperature, we can rely a lot on the fact that the models are good for that and that we have the data from volcanoes to validate it. When we talk about a regional drought or a regional heat wave, there are valuable insights that are coming from the model, but they're much less skilled at predicting extreme events and the kinds of things that are increasingly in the spotlight for being important drivers of the impacts of climate change.
Two little tidbits. One is, it's always in science easy to predict things after they've happened. That's a bias and a problem in all sorts of areas of science. And if I recall right, and one of the panelists may correct me, there was a paper published from Jim Hanson's group, as I recall, the GISS group, about the Pinatubo eruption that predicted roughly the global temperature response to the Pinatubo eruption. And crucially, the paper was submitted before you could see the results. And that says that way back there with the models of the early 90s, people were able to quantitatively get about the right amount of cooling from Pinatubo. And that really says something about how good they are. And I'll give one more tidbit. When I was first a postdoc working on climate models at NCAR in the early 90s, we had essentially a little Fortran module to fake what a tropical cyclone would do, because the model wouldn't itself generate tropical cyclones. And now models do a spectacularly good job of generating the right kind of intensity and spatial distribution with tropical cyclones, and it's not hand-coded. It really is coming out of the model physics. And that's an example of where the models really are, it's clear they really are getting a lot right.
What I would have answered on this is almost exactly what David said a few minutes ago. And I just want to amplify a couple of things there, which is, you know, absolutely 100% agree. We're never certain about anything. We can't use lack of certainty as an excuse, and it's very unclear what's good enough. I think people do tend subconsciously or consciously to put a higher bar on actions that are deliberate than side effects. I think there's two really important framing comments on this. One is people who fundamentally believe in their heart that this is a moral hazard, that either you cut CO2 emissions or you do this. Of course, it's, you know, we have more uncertainty in the world where you do this and don't cut emissions. I think if you view it as this is a supplement, this is something you do on top of cutting CO2 emissions, I think there's actually pretty good reason to think that there is more confidence in what the models predict if you do SAI or some form of solar geoengineering than if you don't, right? If you allow the planet to warm into a regime that we're totally unfamiliar with, that is probably much higher risk, much higher uncertainties. The second real framing comment is if I stick a molecule of CO2 into the atmosphere right now, it sticks around for a really long time. That's not true for sulfate. And the importance of that is if somebody were to decide to deploy, you're not locked in to deploying for the rest of your life. The analogy that I use sometimes is it's like, some people tend to think of this as, oh my gosh, we're gonna have to make this decision under uncertainty. And they're thinking of it like jumping out of an airplane without knowing whether your parachute works. That's just fundamentally the wrong way to think about this, right? You would start small, you would see what's happening in the stratosphere, you would you basically resolve all of your stratospheric uncertainties right away, long before you actually even had much of a climate response. That may be oversimplifying a little bit, but I think those are sort of important framing perspectives.
Yeah, maybe I can add two more things. One thing is, I agree with what previous people said. We do have a good understanding. There are uncertainties that we can do better. I would say we know there are a lot of things we can still improve. That doesn't mean that we can wait for being perfect, as I said, and we'll be never there. We have certainly right now an uncertainty of when we inject a certain amount, 10 teragram sulfate, how much cooling do we get? And that's about a factor of two uncertainty. How much injection do we actually need for a certain amount of cooling, which is something that is based on our still non-understanding on what is the differences between different models. And it isn't even clear if the reality is in that range of what we are estimating. But as David said, if we do simulate volcanoes, we're getting pretty close because we know the answer. And then models can adjust it. So we are not far off, but there's something, I mean, we'll all agree, I think, that research and continued work can help us. The more we can do, the closer maybe we can, the more we can reduce our uncertainties and improve our understanding. So the more research we do, the better we can inform policymakers. And I don't think anybody doubts that. The point, what I also want to make, the second point is when you think about what are the effects, the impacts of climate intervention, it's not like this are the effects. Because climate intervention, applying it depends on various variables, and we haven't talked about it. It depends on really how do you apply this method? When do you start? Where do you inject? What material are you going to use? And what altitude do you want to inject? Do you want to inject first in higher altitude latitudes so we can cool first the poles? Do we want to inject in the tropics? These are all things that when you do it in a different way, you can actually get different answers. And I think that's a big challenge to communicate the effects of SAI, because you cannot say SAI does this, but you have to say this way we are applying it, well, can do certain things. And the problem is really that when we look at the surface impacts, the models are still not agreeing on things. So there's still a lot to be learned on why they don't agree and what are the differences. Just to throw that out as another point.
Maybe
Yeah,
just to offer, just to offer to anyone watching this that wants to play the climate emulator. Sometime back, like some weeks back, Jeremy and I and a number of climate scientists collaborators, Duncan Watson Paris, Daniel Visioni, Ben Travis, Dakota Gruner, and Chris Smith, actually released online a climate emulator at a website, planetparasol.ai, parasol like the umbrella. So for any of you that want to play with it, if you go to planetparasol.ai, it's based on a SAI model by the FAIR, called the FAIR model, and lets you specify how much sulfate do you want to inject, and which SSP scenario, how much CO2 emissions do you think will manage to emit or not emit over the next several decades, and then run in real time based on the scenario you choose, what the forecast average global temperature will be, as well as try to forecast some of the local effects. And maybe regarding the question of how good are climate models, maybe just a high level and to summarize things I think various people have said, I feel like the science of the impact of SAI on average global surface temperature, that feels pretty solid to me, right? Inject particles, reflect more sunlight, planet will be less warm on average. So that conclusion, it feels pretty solid to me. What is less confident, I think various people are saying there's just the local impacts. And I feel like there's a lot more work to be done there to better nail down the local effects, because just as warming has not been even over the last several decades, the reduction in warming or cooling will also not be even over the coming decades if we engage in SAI. And so I think models like planetparasol.ai, but also many others, to try to model this would help us reduce the uncertainty. But I also agree with what David and Douglas and so on were saying, that while there is uncertainty, there's maybe equal or greater uncertainty to what will happen if we go on the current trajectory. And so the of us is
to push back on the framing you used a little bit. So I think it's important to say the following. So first of all, Simone said, if the question is, what is the uncertainty about solar geoengineering or stratospheric aerosols with any kind of conceivable deployment, then the uncertainty is huge because there's so many deployments. It's not scientific. But if you're talking something like the following, say 0.5 degree centigrade global cooling, say 50 years from now, 2075-ish, which would be a giant benefit that we can actually quantify some of the benefit in terms of reduced deaths from heat. And if you're doing it in a way that's pretty even and hemispherically balanced, then you're talking about what we call radiative forcing, the amount of we're changing the radiative balance of the Earth, that's pretty even. And then we're modeling a pretty even radiative forcing against a pretty even radiative forcing from CO2 and greenhouse gases. And the fact that neither of them will likely get the local impacts exactly right doesn't mean they need to make policy, because we made lots of good policy about climate without knowing the local impacts exactly right. And there's no reason to think there will be very strong different local impacts if you're choosing a kind of stratospheric aerosol that's pretty evenly distributed. So I think I don't actually expect really rapid progress in improving our knowledge of local impacts, because there's been a lot of climate science for half a century now, and models have got a lot better. It's hard to make progress, but I also don't think we need to make that progress.
Yeah. I agree with that.
Makes sense. Thanks. It'd be great to now transition more into maybe potential risks of SAI. I think everyone's touched on a little bit of them, but it'd be great to dive a little bit deeper. What do you see as the biggest? Let's start with maybe physical risks, air quality, ozone effects, etc. Maybe speak to these and maybe comment a little bit on what potentially could be done to try to mitigate them.
I mean, I can start again with some of the obvious physical risks. Simply thinking about well, what you have to think about is that we could inject aerosols basically in one hemisphere or unevenly in different hemispheres. And that's because we wanted to mimic a volcano. We just said, okay, this is an analog to volcanoes. We inject like volcanoes in the tropics. But what happens is that the aerosols may go into one hemisphere more than in another hemisphere, so they would unevenly cool the climate. But that what causes then, or a result of that is that you could get shifts in rainfall pattern in the intertropical convection zone. That's the big rain band of the tropics that could shift basically and lead to some droughts in some countries and more rain into other places. And that would be a big risk that people are often worried about. So the question is, how can we prevent those things from happening? And that's why we started thinking about how can we actually inject aerosols in our models in the right way, or gases, that we can prevent it. So we need to really monitor this cooling imbalance and between the two hemispheres, so we can make sure that we're injecting the right way, that shift doesn't really happen so much. We don't want to have large changes in those things. And the same thing is if we inject in the tropics, you have more aerosols in the tropical region, less in higher latitudes. It can happen that you're still getting warming at the poles, right? At the poles, and you want to prevent that too. So what you need to do, we need to be more smart in where we inject. We need to inject in higher latitudes. But this type of strategy, what we're talking about, and there are ways to basically run this in the model, maybe if we would deploy it in a way that we can actually estimate where do you inject the right way, right? You could think models can do this, but it is tricky. And to get it really the right way is still something we really need to look into more, I think. So that's one of the physical risks, I think, that's often talked about, the rainfall changes.
I'm just going to step up just a level in terms of framing about risks. I sort of lump them a bit into four, just to be explicit. You mentioned the physical risks. There's the sort of the physical risks of a responsible, well-managed deployment, doing something hemispherically symmetric and so forth. There's also the physical risks associated with what happens if the deployment is, for some reason, not well managed. So termination shock is something people talk about. If you ever stop, the temperatures go back up over the course of a decade or so. There's the moral hazard one. What happens if people use this as an excuse not to cut emissions? That's sort of a purely societal one. And then the risk of conflict, broadly the risks associated with what happens when people don't agree over the deployment. You ask me personally, I actually think the last one of those, the challenges with how you make decisions, is that's probably the one that I worry about more than the actual physical risks. My reaction would be a little bit the way David just put it, which is that if you're imagining cooling by something like 0.5 degrees, people will talk about, sulfate aerosols, they'll affect ozone, sulfate aerosols that'll come down as acid rain. I think if you anchor yourself and say, well, if we know that 0.5 degree of cooling would reduce lots of climate impacts, what are the actual physical risks associated with 0.5 degree of cooling? My guess is, and it's a bit of a guess, when we've done all of the research, which we have not yet done, we will find that a lot of those are really just not that big.
One other thing that might be helpful to think about just a little bit is how people and countries in different parts of the world perceive risk and what they perceive as unacceptable for their own future. And if a country accidentally released a nuclear device that destroyed another country, that would be considered totally unacceptable by any standards of international governance. And the challenge that people are really trying to tamp the risk down close to zero is that a deployment of stratospheric aerosols could result in fundamentally unacceptable impacts on one country or one region. And Simone talked about the consequences of a shift in rainfall. And we can imagine another big set of mostly pretty unlikely risks of extremes, especially extremes of low precipitation, of kind of civilization-ending drought that are being explored through lots of different efforts. It looks like the probability of anything like that is very, very small with the kind of sensible deployment that's being discussed. But how low does that risk need to be in order for people to have the confidence to say, this is something we could really consider? And that's an important topic. It's not really resolved in international discussions, but it's one that we need to think hard of, not only because there are these, you can think of them as distributional risks from stratospheric aerosols, but they're profound distributional risks from the climate changes as well, with the people in the poorest countries, the ones that are the most vulnerable to climate impacts, already experiencing the most. And we almost don't have a vocabulary for discussing how we trade off the high and rising risks of climate impacts that are really serious against the low but not precisely known risks of the stratospheric aerosol deployment.
I want to maybe pick up the thread of people's risk perception varies, of course, but picking up on something Andrew said earlier on, I forget exactly what you said, Andrew, but that pointing out that there's lots of public concern about this technology, or distrust or dislike of it. I think it's always very hard to figure out what the public knows just from watching some media or social media or what have you. And you really need empirical research that goes and asks people. And there is now some of that. And it's even done it on a global basis. There's a couple papers that are really asked on quite a widespread basis what more regular humans, not a bunch of us on this call, think about solar geoengineering. Plus, there's been some versions of this that ask climate negotiators that. I point to Astrid Dannenberg's paper. And I'd say a general result of those surveys is first of all, a robust result now from 3 different surveys is people in the poorer parts of the world that are more threatened by climate change take this technology more seriously than people do in richer countries in various measures of seriousness, but are more favorably disposed. And the second thing is that this is a bit more fuzzy, but I think it's impressionistic, but I think, because it depends on exactly how you ask the question, but I think the average people you ask the general public are much more favorably disposed to certainly research on this topic and maybe to implementation than are kind of elite people in the climate conversation, to be blunt. And so there's a kind of disconnect between where the high-level climate conversation, the level of the top newspaper reporters or most active climate scientists are, and what people think.
I feel like there's something to be said for considering what are the conditions under which we would be comfortable with a very small scale implementation. It was interesting that when David was running the ScopeX project, that Dan ran into issues. Maybe you can tell that story if you so please. But I think part of me wonders, what is the risk of a very small scale implementation, which, as Douglas mentions, will follow the atmosphere over some period of time, and it's not irreversible. And to some extent, I think someone mentioned termination shock. The reduction of sulfate pollutants is already causing, like a minor termination shock on our planet today. So now the flip side, though, is a very small scale implementation would be very difficult to have any measurable impact on global temperatures, but we could test out other things through such a process. So whether at some point it becomes deemed responsible to do a very small scale injection of sulfates as a step to improving the science, and how much we could actually learn, right, from such a small implementation. Those
I think
questions.
this is getting into some of the confusing topics. So to be clear, the ScopeX experiment would have had 0 alteration of global temperature, and even its strongest critics, the famous letter from the Sami Council that encouraged the Swedish government to kill the project, that, to its credit, that letter conceded that there wasn't a physical risk. So I think it's agreed by essentially everybody that there wasn't physical risks. But also, I think it's important to say that in terms of what are the uncertainties in the science, maybe we're deluding ourselves, but us in the kind of climate modeling science world don't think there's really any uncertainty that if you reflect sunlight, the planet will cool. That feels like really basic physics, or even that aerosols reflect sunlight. Those are things we know. Our uncertainties are about this distribution of aerosol sizes, how aerosols interact with each other, how they interact with the background chemistry. Those are things that experiments would go after. And so, in fact, in the experiments that I've been involved in thinking about, we often weren't even going to bother to measure how reflective the aerosols were directly because it's not an uncertainty we care about that much.
Maybe one thing to think about also the effects of small injections. You know, we constantly actually have volcanoes inject aerosols into the stratosphere, gases, to an amount that is just much larger than any aircraft, or any experiment would do. We just had a large injection that was the Hunga Tonga injection 2022 that was 0.4 teragram. We're talking about when we cool a degree or half degree, maybe 10 teragrams, so much smaller than that. But it can be measured. But those is still much larger than any experiments that somebody would do to actually observe the behavior. And in fact, those volcanic eruptions are really great to look at the science and observe, the movement of aerosol, observe the behavior and so on. If we had more resources actually to observe them and would put more effort into, I mean, there's a lot of people looking at that, but much more could be done to really make use of those smaller injections. And in terms of termination effect too, I mean, yeah, Mount Pinatubo, most of the older people on the call and in the audience have survived Mount Pinatubo, right? If it cooled 0.3 degrees or half a degree, if that's the amount we want to cool with SRM, and we want to actually slow down or phase out some intervention like that in a small amount, it's not like it would be catastrophic, right? There were impacts, but we do have examples of smaller termination effects as well, right? Or of volcanic effects starting. It's just something to keep in mind. It's not like completely unexplored territory that we're talking about.
Very much not. The first paper that had a bunch of the science of stratospheric aerosols was published in 1960. I think in thinking about why, I think maybe thinking about people on the call might think maybe all you scientists are overconfident. I want to offer the following. This isn't a law of nature. I'm going to tell you how I think. If I hear something from a very small group of scientists, maybe all at one institution, who say they've got some cure for childhood leukemia or whatever, and it's just published in Nature, but it's only 2 years old, I might be a little skeptical, even if they're really well intentioned. It's just people are wrong in science sometimes. But if there's some piece of science that's like 50 years old or 30 years old and has been pretty widespread around the planet, that is, the scientific community's many different groups have worked on it for a long time, then the probability of it being really wrong is pretty small. And to me, while ideas about solar geoengineering are new and shocking to lots of people, the science on which they rely, the science, for example, of aerosols in the atmosphere and response of the atmosphere to aerosols, that science is a scientific body that is tens of thousands of papers by many investigators around the world over something of order half a century. And that's the reason that I think we can be reasonably confident that we can predict with uncertainties, but predict what would happen. And also it's a reason why, in fact, while I'm very keen on more research, I don't expect more research to dramatically enlighten us because there's been all this research already.
One thing about the inaction is I think earlier this year Wake Smith published a paper from Yale on his assessments on how long it might take to go from a hypothetical decision to go to an actual at-scale implementation. And I think he was estimating something like a 2-decade interval between a go decision and when we may attain a certain target cooling. And I think there is
But a very large amount of cooling, it's important to say. So Wake and I work closely together, and I think Wake was worried that people thought it was too early and too easy. And he wanted to publish a bunch of papers to caution people it's not that easy. I think it's complicated. That's why Wake and I worked together to publish that paper that was in Technology Review that suggests doing it with existing aircraft. I think Wake is right that if you did it with standard contracting and standard rules, and you're going for cooling of the order of a degree C, then 20 years is the right answer. But that's a lot of ifs that to me don't apply that much, because I can say that I would absolutely oppose with every fiber in my body going for something as fast cooling as 1 degree C in 20 years. It would be crazy.
Yeah.
So I think that there's a sort of overstatement there. I think the point is we could start ramping up in a meaningful way. It's technically possible to do that sooner than 20 years.
I agree with that. I felt 20 years was a pessimistic estimate, but also want to point out, I think we have a lot of engineers on this call, but one of the set of important engineering challenges would be to design the aircraft as well as the equipment to inject the aerosols. How do you manage large quantities of sulfate high up in the atmosphere if its SO2 is corrosive? We do have aircraft that can fly up to the stratosphere, but what aircraft can carry large amounts of sulfate and operate on a continuous schedule? So I actually foresee, if ever society writ large decides to proceed with this, there are significant technical engineering challenges as well to do the implementation.
I agree, and I'm eager. People who are interested, feel free to reach out to me. Wake and others are starting to work on this and bring in aircraft engineers. And I think there's a lot that can be done, short of actually building any aircraft, doing more serious engineering trade studies with aircraft engineers to try and understand how that would work and what the range of options are. It's really important. I agree.
But it also is pretty clear, even at this point, that we're not aware of any technology showstoppers that would make it impossible to deliver the quantities of aerosol that we're talking about. Substantial engineering challenges that would take some time, a few years and possibly a decade or more to really get addressed, but nothing that looks like it's a showstopper.
I mean, maybe going back to the risk, we talked a little bit about the experiments, right? And the short-term ScopeX or other things. For the long-term application, there is still a lot of unknown in terms of really the effect on the surface and on the biology, on the societies, and the ecological system. Because even though we can talk about volcanoes being some kind of analogs and we can observe things in the stratosphere and the cooling, what we can't observe from short-term eruptions is really what is a long-term effect. And I think that's one of the things that we haven't explored that much, and there's a lot of more work to be done to understand on how will it affect actually algae in the ocean when you change UV or scatter. Will it be beneficial? Will it be worse? And for whom and when and what? And that's really things that we really have to look into still a lot.
I wonder if it's nice speaking with on this panel where all of us share a cautious but scientific view to what looking at the reality of SAI and what, if anything, should be done. I kind of wonder what this discussion would be like if we had some of the most strident critics and what they would be saying.
I mean, I think there's a subset of critics that are primarily concerned about the governance challenges. There's certainly some critics that are much more just this is hubris and humans shouldn't be doing this at all. There are some critics that are concerned about the physical uncertainties, although I would say quite often when you really drill in with those people, quite often they have a assumption built into their thinking that it's a sort of a moral hazard, and so they're not necessarily always really worried about the physical uncertainties as much. That's maybe a bit of a guess, but the really most strident critics are on the governance side.
I think we're in an era where justice is increasingly central to the way people think about the world. And the core justice issue in the climate crisis is that the rich world has been releasing vast amounts of heat trapping gases to the atmosphere for more than a century. And the justice-based framing is that they need to do something about it. And the standard answer has been, and that means to cut those emissions, to backtrack on the things they did that caused the problem. And it's a powerful argument if you think from a justice first perspective, but it also leaves out the possibility, and this kind of comes back to the 4 overall strategies that David talked about earlier, that relieving some of the impacts of climate change might be possible as a strategy that complements the cutting of emissions. And I think that whether or not you have a mindset that's open to doing more than one approach to tackling the climate crisis probably is the biggest decider about who's a critic and a skeptic of this, and who's willing to think seriously about it. From the perspective of the justice-centered, you have to solve the problem by undoing the bad you did. If the solar atmospheric injection doesn't help. If you're willing to look at several steps, a portfolio address the problem, the landscape looks different.
I'll offer a justice comment. One thing to say is, think about, first of all, just about the justice of deploying the solar geoengineering. I think it's important to think of 2 categories. There's more than 2, but 2. One is distributive justice, which is what's the actual distribution of benefits and harms of the action. The second one is procedural justice. Who should get a say in the decision, and how are the votes, if you like, distributed around the world? And both of those matter, but they're not the same thing. So it's possible to have something which, in a distributive justice sense, is actually beneficial to some of the world's poorest, and there's really quite strong evidence that solar geoengineering would be. The one paper that I think Doug's an author of it, that quantitatively looked at the impacts of solar geoengineering on global inequality, found that it would dramatically reduce inequality in inter-income basis, and that's for the reason it's the huge injustice of climate. In hot regions, climate reduces economic growth, and those are often poor regions, so that's why climate change tends to exacerbate existing inequalities. And solar geo, by the same logic and the same econometric analysis, would tend to reverse it, which is a really, I think, a very important reason to take this seriously, that a lot of the benefits would likely go to some of the world's poorest living in hot countries. But that's not the same as procedural justice. There's a separate question of who gets to decide. And people would rightly say that there's an arrogance in a person like me right now sitting at 53 degrees north latitude and a pretty wealthy person talking about what is in the interests of the world's poor, because in the end, they need to make that decision. And that's a separate procedural justice question about who makes a decision, which is separate from who actually benefits.
This is all related to the conversation about governance. And I think someone in the chat actually asked a nice question that I'd like to raise here, which is, my limited understanding is that solar geoengineering doesn't respect borders. If one country were to deploy stratospheric aerosols, it will impact others. What type of governance would you want to see over solar geoengineering efforts to ensure a coordinated, controlled, positive outcome? Any thoughts on this?
I'll try. So let me just say some disappointing stuff. We use the word international law, but it's not like domestic law because there isn't a sovereign. This is like what you learn in International Law 101. There are international laws that really do work to settle disputes between states, but it's just not like national law in the sense that we don't have a sovereign and we don't have the power of enforcement in the same way. And it's just a sad fact that humanity lacks a method to ensure the outcomes are good in that way. And that's true for all sorts of problems that we face that are distributional and international, that whether that's vaccines or new chemicals or new technologies or satellite networks, all of these things have impacts that go beyond national borders in different ways. And we don't have a way to ensure that, some kind of justice principle is obeyed, that, nobody's made worse off and people are made better off. But it's also true that we have muddled through on lots of topics. And my view is that in practice, this will be done by a set of countries, North and South, that have some kind of loose framework for how to go forward, and that's coupled to some kind of global architecture that doesn't have enforcement, that the actual actors will be a coalition, but that a global mechanism such as the UN Framework Convention on Climate Change is also important. But the sad answer is we don't have a system for this or anything else that ensures a good outcome.
Yeah, I think the current biggest problem we have with taking steps toward the kind of informal governance system that David is talking about is that we're not seeing countries call for this. We're not seeing them call in a full-throated way for either the research or the deployment. But if that starts happening, when that starts happening, especially if it's vulnerable poor countries that are calling for progress, I think that really becomes a tremendously powerful enabler for setting up the kind of informal governance that can allow countries to participate in a meaningful way. Doesn't require everybody to be on board, but it really has to be stimulated by that call for action from the poor countries.
I think that is precisely correct.
Yeah, and maybe putting in perspective how we deal with the climate problem, right? And there's a lot of call for reducing emissions, but many countries are not committing enough. And I think that's one thing where the resistance is there, that people want to commit to something like solar geo, because the idea that you haven't committed to reducing greenhouse gas emissions is not, it should be maybe mandatory before you think about actions of solar geoengineering. It's an argument that makes sense in some way, because you could go into this idea of the slippery slope, that you actually, or that idea, the moral hazard, sorry, that you actually continue emitting while you have started this. And I think that's where often, or that some of the resistant and many people feel resistance about going in the direction because we haven't really started climate actions. But I wonder what other people think. I'm not a governance expert on this.
Well, just to say, I think you're right. And I think Chris said very well, this sense of justice that the people who did the pollution ought to pay, which I think is correct. And I support the idea that there should be payments for loss and damages, because the damage was done by the historical emissions of CO2, but that's ought to be separate from the decisions about SAI. But I agree that's how people think. What's not clear is what actually ought to happen going forward.
This might be a good time just to remind people of a comment that David made earlier about the progress we've made on emissions reductions. And even though emissions are still going up, 10 years ago, we talked about a business as usual future ending the 21st century with a global average temperature between 4 and 5 C above pre-industrial. And now we're talking about an end of century future with the kind of commitments that have already been made between 2.5 and 3 C. It's an amazing amount of progress we've already made. And I think it speaks to the fact that we're not in a world where nothing's been done about climate. Where we are is in a world where not enough has been done about climate.
Yeah, I mean, some of you will have heard me say this before, but global spending on clean energy, which is mostly solar, wind, and electric vehicles, is now around $1.7 trillion, $1,700 billion a year. Not all of that is motivated by climate, but it's stunning. It's that's tripled over just a relatively small number of years. It was for a long time about 300 billion a year. It's an extraordinary number. And I don't actually put much stock in the commitments of politicians to things that will happen 50 years from now because they're not bound by them. It doesn't really mean much. What I do put stock into is the actual flow of capital into the ground and the fact that solar has got extraordinarily cheap and that there now is a clear pathway to decarbonize the world. Doesn't mean it's easy, but there's a pathway.
Actually, that's a good point. One of my teams here at Fund, we do some work with AES, which is the largest producer of renewable energies for data centers, and watching the way that AES rolls out large scale geo solar battery storage. I think to those of you that haven't seen the giant solar farms and industrial scale production of renewables, the progress with a battery storage, especially grid scale battery storage, is really quite encouraging.
I think there's been a few questions in the chat about how SAI might compare to other intervention strategies. Anyone speak to those and comment on that?
I think Dirk, Dirk, did you want to say something?
You can jump in first, or I can jump in first.
I mean, Dirk made the point earlier, SAI can act faster than other interventions like carbon dioxide removal. Carbon dioxide removal is something that needs to be ramped up. That will take a long time before it actually can act and reduce a substantial amount, and it's still quite uncertain in terms of costs and other things. While we do know, as we have already discussed several times, that at least we know that all the models show we can cool the climate with aerosols in the stratosphere. How much exactly that will be and how it actually looks like is still to be looked at in more detail. But it is faster and it could be done, and that's why it's different as a method until, a temporary, and people talk about stopgap measure or something, temporary method until we actually get the concentrations to levels that are safer for the climate again.
I would also point out there are other ways of reflecting sunlight. We spend most of our time talking about stratospheric aerosol injection, applying, as we've said, we know with 100% certainty that would cool the planet. The idea that has had the second most attention is probably marine cloud brightening. So if you spray salt water into the right type of clouds over the ocean, for the same amount of water, you now have that distributed over more particles, more droplets, and you reflect more sunlight, so you can make those clouds brighter. They're different. They're actually quite different. They're conceptually the same in terms of reflecting sunlight. Marine cloud brightening, I would say, is certainly it's much less well understood. Cloud aerosol interactions are one of the biggest uncertainties in climate change. It sounds more benign. We're just going to go spray salt water into parts of the ocean that are a long way away from where anybody lives. And maybe there's more of a social license to do that. But if you try to cool, there's only the right type of clouds over part of the ocean. So if you put a lot of forcing over small areas, and then the planet does its best to redistribute that cooling, you are going to get bigger shifts in regional climate. As David said much earlier, if you have a relatively uniform layer radiative forcing from stratospheric aerosols compensating a relatively uniform CO2 radiative forcing, a reasonable understanding of the regional effects. So I'd say marine cloud brightening is less well understood, and it carries a different set of risks. You could in principle do something in space. That is not something that's going to happen in the next decade or 2 decades, I think. I think David would agree that's probably more plausible than many people assume, but it's certainly not as near term, and it's more expensive.
I certainly agree. Let me add one more thing. I agree with everything, and Doug said it exactly right about the scientific uncertainties about MCB, but it's also true that climate engineering is both about climate science and about engineering. And there's an engineering sense about, well, we can all argue a little bit. There's just no fundamental question you could put sulfur compounds in a stratosphere at 20 kilometers and you could do it. And in the following sense, no new technological breakthrough is needed, no new development of technologies. You could contract with existing suppliers who would give you performance guarantees to go do it. They might take maybe Wake's right, it would take 20 years, maybe a little shorter, but there's no doubt it could be done. In that sense, it's a development challenge, but not a research challenge. MCB is not like that. For MCB right now, the best sprayers are about 3 orders of magnitude, a factor of 1,000, lower in number of particles per second than they would need to be for large-scale deployment. And that means that MCB is not in a place where you could just say, go contract with some engineering firm and just go build the sprayers for deployment today. We actually don't know how to do it. I am sure somebody will figure it out. There's some wonderful people working really hard to develop better spray systems. I expect it will get solved. But it's important to say it's very hard to predict research in a way that's different for deployment, for development. If you've got something solved in a research sense and you're just talking about developing it, we have some sense of how long those things take and what they cost. But for MCB, there's some sense in which we don't really know how to do it now. And I think we'll learn, but it's a little more theoretical.
And when we talk about solar geoengineering as part of a portfolio of other steps, and we're going to cycle back to the things we've already talked about, but it's important to start this conversation with the note that even if we restored temperature to exactly the pre-industrial level, there would still be consequences of the greenhouse gases we've already emitted. The ocean is much more acid than it was. There are profound consequences of that. The spatial distribution of climate would be a little bit different. So we really need to figure out a way to solve the greenhouse gas problem, even independent of an effectively deployed solar geoengineering strategy. And that means we need to have the cut emissions component. We need to have the CO2 removal component that David spoke to earlier. And we need to have the adaptation component because we know we're not well adjusted to the temperatures we're encountering even now, and we're going to face increasing challenges with warmer ones. So that co-deployment is going to be essential no matter what, and it's got to involve the cutting emissions, removing the CO2, and adapting in addition to whatever level of solar geoengineering we decide to deploy.
Yeah, maybe adding to this, the risks are increasing. If we want to do SAI or any form of solar geoengineering, the more greenhouse gases that we want to counter with that approach, right? The more injections or the more of these approaches we need, and the higher then again the risk of, let's say, the termination effect. If we want to actually counter 2 degrees of warming, a termination effect would be much more risky than if you just want to balance 0.5 degree of warming, right? And it says if we want to stay at a certain level or if we want to do a certain amount of geoengineering, the question is really what are limits on how far do we want to go? Is 1 degree okay for limiting reasonable risks, or can we go and cool 2 degrees of warming, or maybe 2.5? These are all questions that need to be explored, but surely it shows, at least for initial research, that the less we have to do, the smaller the risks are also with those approaches. And that motivates what you're exactly saying. It isn't a way out of the problem. It just would potentially help to mitigate the effects, the impacts in some way, if we can show that it really reduces most of the impacts.
There should be nothing shocking. Of course, Simone's exactly right. Nothing shocking about that. Complex, big social problems like climate change very rarely have a single solution. And of course, we have to cut emissions, but emissions is not the solution to climate change, because if we eliminate emissions, the climate change is still there. And none of these things individually is a solution, but some combination of them is a lot. Some combinations will be better than others, and action is much better than inaction.
I want to share something that I saw from AI that gives me hope. About a year and a half, a little bit over a year ago, there was a somewhat, I think, irresponsible statement that got a lot of PR coverage saying AI is like nuclear weapons, or made that analogy in a very irresponsible way, and it actually scared a lot of regulators in Washington, D.C. and other nations' capitals to be, kind of fearful about AI. But what I saw was that on average, as people talk more about AI and learn more about it and better understood the science of AI and what it can and cannot do, a lot of the unnecessary fears went away on average, and there were definitely exceptions. Didn't happen for everyone, but as there were more conversations, many people, certainly in Washington, D.C., but other nations as well, came to a much more rational view, with exceptions, but much more rational view about AI. And seeing that happen in AI over the last year and a half makes me cautiously optimistic that with more conversations like this one, if more regulators, citizens kind of talk about SAI, that society maybe could evolve to a rational view on this and make sound decisions around this. So I think those ongoing conversations are at multiple levels, multiple places of society seem important to me. It makes me optimistic we'll get to a good place.
I think the big challenge of our current moment in the conversations about solar geoengineering is really hard to figure out how to do the initial steps of confidence building, that there's a research agenda that can be helpful, that there's not a nefarious plot behind the conversation to drive a particular outcome, that the community of researchers is operating in good faith to provide the critical information to address the questions that have been raised, and that there's a genuine commitment to developing a governance model that's broadly acceptable. And if we can figure out how to get some of these first steps going, the kind of iterative improvement that Andrew describes has some possibility. And I think there have been some positive signs of calls for research and increasing investments in research by government and private actors. A whole bunch of amazing papers have been published by Simone and Doug and David and others. And we are seeing more and more of the pieces come together that will be required to have a global conversation that heads in a constructive direction, like I agree the conversation around AI has. But we're not quite there yet.
We're in the last 10 minutes here. Oh, sorry. Did you want to say one more thing?
Yeah,
Andrew?
okay, quick. It was interesting. In the case of AI, there was scientific progress. People did figure out how to make AI models less safe. There was a lot of red teaming exercises to try to explore if there are ways it could be used for harm. So there was some scientific progress, but I would say a lot of the progress was actually made not by the action on the science or the engineering. It was actually I would say the vast majority of the rational decision making around AI was driven by just conversations and improving understanding, and then a little bit, but the smaller fraction was by taking those concrete forwards that you mentioned, Chris. So hopefully, for SAI, we'll have a roadmap for getting a broad shared understanding toward rational decision making. But sorry, Jeremy.
Yeah, no worries. So yeah, we're in the last several minutes here. It'd be good to answer a little bit more of the audience questions. There are a couple on AI. So while we're talking about AI, a couple of these questions are about AI's role in understanding solar geoengineering. Anyone want to speak to that?
Well, so I think AI climate modeling has an important role to play, already has, although there's a question of whether we'll ever get enough data to use AI explicitly to model the impacts of geoengineering, because we don't have that interventional data. We do have some data from volcano eruptions and so on. And then I feel like various of us are excited about building climate emulators, where right now many climate models take a long time to run a simulation. And I think a lot of work done by many groups to use AI to model or to emulate much slower physics simulators lets us get really fast running models that allows us to very efficiently test out different scenarios. What if you inject this much at these lab, here, and I think those are important things. Oh, and can I say, I actually saw in some of the questions, people are asking about AI's contribution to climate change. Maybe let me just speak briefly to that as well. So it turns out that data centers do use a lot of energy, and AI does use a lot of energy. But it turns out that if you look at the CO2 emissions associated with, say, a single Google search, I think that's been estimated at 0.2 grams of CO2 emissions per web search. And in comparison, I estimated if I drive my car to the local library to look up something, I would generate about 500 grams of emissions. So doing a Google search, even 10 or 100 Google searches, is actually much better than me driving to the local library, at least from a CO2 perspective. But the core problem is so many people do Google searches and use the internet in other ways, that in aggregate it does add up to a significant amount of emissions. But I think that the concentration of compute and data centers gives us better tools to drive down the emissions associated with per unit value created or per amount of work done. And this is not to say we don't need to, we do need to take seriously how to continue to make data centers more efficient, drive down emissions and so on. But I find the work that many large cloud companies are doing to have, for example, hourly match renewables to power data centers. And really, we've got pretty good at optimizing data centers. These are positive signs. And then if the measurement is amounts of work done per unit of emissions, I think data centers actually do quite well there. But the problem, of course, is we do use them so much that net they do end up contributing measurably to emissions.
And what we need to do is transition to a society that's fundamentally electrified. We have a vision of how to get electricity without emissions, and are making spectacular progress on that. If the residual fossil-driven electricity is contributing to emissions from Google searches, that's something that we're on a trajectory to fix.
There are a couple of other questions about economic considerations of SAI. Pretty broad, but any thoughts on that?
Yeah, I was noticing that one in the chat. So this relates to the paper actually that Doug was, I believe, an author of the economic inequality paper. So in the last decade or two, there's been this real rise of quantitative econometric driven estimates of the impacts of heat, both on economic growth, economic productivity, and also on mortality. And so we know that in really cold days, mortality goes up, and in really hot days, mortality goes up, and that's true in different places. And we now have this really large data sets that allow us to do a pretty good job estimating how heat changes mortality. And that's quite different from, Andrew started off talking about, numbers of people who are dead by the, by attribution, formal attribution from coroners, I guess. We actually don't look at that in these econometric studies because we don't really know what those things mean. What we look at is the all-cause death rate, and then we look at various factors and pull the data out. And that's become quite robust. It's not my work, but it's the work of many people in the climate impact and econ community made enormous progress, like Michael Greenstone, my colleague at UChicago. And same for economic impacts. And that means we can really begin to say something quantitative, both about, forgetting solar geo for a second, about the quantitative impacts of climate change on growth in the poor world and about the gross inequality, the stuff I said before. We can say that quantitatively, which is exciting, but also for solar geoengineering, we can now use those models to say something quantitatively about how many less people would die in a world with solar geoengineering because there was less heat, and also how much quicker economic growth would be, and those both matter.
Let me just say that it gets back to these distributional and the procedural issues that we've been talking about, that for many people, it's not a question of whether on aggregate we save 1 million lives. It's a question of whether by deploying solar geoengineering, we're directly responsible for the deaths of 100 people in an area that experiences a drought. And we need to be thinking really hard about the balance between the aggregate well-being and the well-being of the groups around the world that everybody should care about.
The only other economic comment I would make, just in case it wasn't clear, is the actual direct costs of implementing something like this are basically so small that you can ignore them. That those are not going to be a factor in whether or not one chooses to deploy. I don't mean by that any rich person could go do it, because you actually have to have access to airplanes and air bases and stuff, and that requires nation states. In fact, it requires superpowers to some extent. But it's that piece of the economics is not the direct issue.
Great. So we are just about at time here. I think that's where we'll end it. So thank you so much to all the panelists. Again, really appreciate your taking the time to speak today. And thank you all to everyone who's joined remotely. Yeah, thanks so much. Hope everyone has a nice rest of their week.
Thanks, everyone.
Thank you.
Thank you.
Thanks.